Now, Dennis, I need to ask you, have you done the reading and the Seneca exercises on electric and gravitational fields?
Reading, I'm not sure.
Have you done any of the tasks that I've given you?
I did one, but I don't know what part is it like.
Right. Okay.
I know.
Well, where we're at the moment, we've kind of done a lot of work with gravitational fields. I suggest you go back over your tasks and you sort of make sure you're working through them.
Okay.
What we're going to do today is we're going to compare gravitational fields to electrical fields, because we started to look at the properties of gravitational fields. We finished gravitational fields, and then we started to look at electrical fields. And the work from last week was very much the kind of work whereby that's better. Was very much the kind of work whereby I started to spot some similarities between them. So we've got a few different things. So, for example, if we take two particular forces, gravity and electrostatic forces, you start off with the idea that we can build fields. So, for example, a gravitational field where you've got a flat sort of surface, gravitational field lines show the direction of a unit mass, like that, which is almost exactly the same as electrical fields. Okay, so this shows the force on a mass, and this shows the force on a positive charge. So, for example, if you've got a gravitational field, you've got a point or a circular gravitational field that acts like a point source, you know that everything in free space, everything with mass, is going to be attracted radially to that planet, to that particular object, usually a planet or a moon, because you need a lot of mass. The only difference is that when you have an electrical field, imagine that's a positive mass, the equivalent to electrical fields is charge. So if you have a positive charge, the big difference is not the shape, it's the direction of the field. Okay, Dennis, I'm going to ask you a question now. What I'd like to ask you is, what would be the direction of a force and a positive charge in this electric field, in the electrical field, in this electrical field here?
Right, direction will be from positive charge to negative.
Right. So it'd be, so what do you notice is different between the electrical fields and gravitational fields?
Electric fields is between positive and negative charges.
Yeah. Okay.
Gravity between the mass and planet, maybe, I don't know.
Well, if you look, the gravitational forces and gravitational fields are always attractive. You can't have gravitational repulsion. The electrical fields, they can be repulsive. So direction takes into account. Now, if we think about the forces, we know gravitational force. Dennis, the gravitational force is the weight. How do you work out the weight of an object if you know its mass?
mg.
mg, yeah?
I know.
Which is the
Yeah,
mass
mg. Yeah.
times g, the gravitational field strength.
Yeah.
So if we look at electrical force, how would you work out electrical force if you know the charge of an object and you know the electric field strength?
I think Q, like
Yep. The charge multiplied by what?
I'm not sure.
Well, it'd be the electric field strength. Do you remember the previous lessons before lockdown started? We did some work on electric fields.
All right.
Well, we learned that was electric field strength. So we can start doing some basic analogies. So if we start to think about the electric field strength, if what we can do is we can start to realize that the mass in gravity is analogous to the charge. Okay, we know that gravitational field strength is analogous to the electric field strength. Okay, and everything else then starts to fall into place, because what we've been studying before with gravitational field strength is we know that the gravitational force, if you've got a point source, if it's a radial field like this one, you know that it's given by G times the product of the two masses divided by R squared. Okay, so if we look at it, if we then take our analogy, want to work out the electric force from a radial field, from a point charge in a radial field like this one, what do we replace the masses with, Dennis?
No, Q.
Yeah, you replace it with charge. So if you've got two charges, let's say one charge, two charges, it can be Q1, Q2, but I use Q and big Q and little q, divided by, well, the radius is still the same. It's following exactly the same rule.
Oh, okay.
But what's this here? It's a constant. So that would be some kind of constant.
Yeah.
Okay. So we can then start to play with a lot of other things. Well, that constant for a radial field is actually the product of the two charges divided by 4. That constant is 4 pi times epsilon naught r squared, where epsilon naught is the permittivity of free space. Okay.
Yeah.
So, but that factor there, that 1 over 4 pi epsilon naught, that's just a constant. And so because that's a constant, it's following exactly the same rules here. And so this is actually what we call Coulomb's law. Now, the beauty of this is we can take this further. We can start to do some other parts of this analogy. Because we've just looked at forces. Well, what about field strength? And again, we're looking at a radial field. Okay. Now, if we've got field strength and radial field, what gives you the field strength from a radial field, Dennis, for gravity?
9.8.
Yeah, that would be it on Earth, on the surface of Earth, but there's a formula for radial fields like this one, where the further away you go, the weaker that G is. And also it's dependent on that mass. Well, the way we can work it out is we can take Newton's law of gravitation. If you know that the force is mass times gravity, the m's cancel, and we end up with G equals the gravitational constant times the mass of the planet divided by the radius from the center squared. So we end up with G, big M, over R squared. Now, if that's the case, we know the electric field strength, which is that's in newtons per kilogram. This is in newtons per coulomb, because the charge and the mass become analogous as you swap to different fields. So if we use our analogy, Dennis, what do you think would be this formula here?
Can you show me like last?
Yeah, sure.
What's this?
Is it that bit you're after?
Yeah. So. Oh, it's equal charge in the top, like divide by 4p.
Q over 4 pi
by
epsilon naught.
And what was it?
Well, what's it on this side?
Ah, right, yes. Right.
You see, the whole idea is that we can use our analogies. We know that the gravitational field strength is the gravity analogy to the gravity analog to electric field strength. So the difference is what causes the field. With gravity, it's mass that causes the field. With electrical fields, it's charge that causes the field. So everything else works the same. You've got some constant. Here in gravity, it's G. In electric field strength, it's 4 pi epsilon. Well, it's 1 over 4 pi epsilon naught. Okay. Here we've got the mass. The analogy to the mass is charge. And then it's the same rule, but it's proportional to 1 over r squared, the radius, the distance from the center. Does that make sense?
Yep.
Okay. So the next thing to do is to then start to look at some other analogies. Well, some of the other field strength work that we've done before, we would have looked at potential energy. Now, potential energy, remember, for gravitational potential energy is the work required to take an object well, that would be with mass, from infinity to a point, a distance r from the center. Okay, so if we take our exact analogy here, we could say the potential energy for a radial field is the same thing. It's still work because it's still energy. The work required to take an object, it's a charged object from infinity to a point, and it's exactly the same. The difference is it's charged, isn't it, Dennis? Now, if I take that into account, if I want to work out the gravitational potential energy, I know that it's minus big G times M over R. Okay? Does that make sense?
Yep.
So, bearing that in mind, what would be the analogy for electrical energy, electrical potential energy?
The same, like minus. It's minus.
Minus.
The same.
So what things we've got to transpose here? We've got the constant. What's the constant?
Epsilon.
Is it?
Yeah, 4p epsilon.
Right, it's 1 over 4 pi epsilon naught. So what else have we got to put on there?
Minus.
Right.
And
Remember, let's go back to our original initial fields. What did we say was the difference between these two fields?
I said I know I didn't say about like
What's the
I said
difference?
about
We've got a positive mass here and a positive charge here. So each one shows, this one shows the direction of force on a mass. This one shows direction of force on a positive charge. What do you notice is the only difference between these two?
They have opposite direction, like
right. The direction's opposite. Yeah. So
opposite.
Let's imagine you were taking an object. You've got a planet with a mass big M, and infinity is way off the page. Now, if you take the object from infinity to a point, the distance r from the center, okay? If you're taking the object from infinity off the page to here, are you getting any? Are you having to put energy in, or are you getting energy out?
In, I guess.
Are you? Are you having to do work? Well, if it's an attractive, the gravity is always attractive, isn't it? So it'll be the gravity that will be pulling this object over here. So it won't. So it won't be anybody doing work on it. It will do work, which is why in our formula it's a negative number, because actually it doesn't do. You don't. It says work required. The work required to take the object from infinity to a point distance r, but it's a bit. But it's not actually. You're not actually planning to put work in. It's doing the work. Okay. Does that make sense? So the negative sign disappears. So what's left here? What else have we got to add here? Well, with electrical fields, what's the analogy to the mass?
Charge.
Charge. Okay. And what's the last bit?
Radius.
Not minus. Remember, this is going to be positive, isn't it? Because if you take a positive charge and you take another positive charge and you bring it from infinity to that point, if that's a positive charge, they're going to be trying to repel. So you're going to have to do work. So it's going to be positive work done. But what's the last bit that I've got to put on this formula?
Radius, no?
Radius, yeah. 1 over the radius. Yeah.
Yeah, right.
Okay. So the same thing works every single time. So the actual, this is why I taught gravity before I taught the electric field strength, electric fields, because the behavior is identical every single time. Right down to things like, right down to things like the idea that the potential, gravitational potential, which is the force, the work required to take a unit mass from infinity to a point of distance r, follows, oops, I do apologise, I missed a tiny bit there, there we go, follows exactly the same rules. So that would be Q over 4 pi epsilon naught r. Does that make sense?
Yes.
Right, so it's following exactly the same rules. And we do the same thing with units. We know that gravitational potential, that is it's an energy per unit mass. So that would be joules per kilogram. So what would be the analogy here with electrical potential? It would be joules, because it's still energy, but this is now a unit charge. What's the unit of charge?
Unit of charge. I know. Oh.
Well, the unit of charge is the coulomb. So if you've got joules per kilogram there, that's going to be joules per coulomb. Now you've done some electrical circuits with Mr. Welsh. With joule per coulomb is the definition of what?
No.
There's a definition of the volt. 1 volt is 1 joule per coulomb. Yeah? You probably know that energy dissipated in an electrical circuit is going to be the charge times the voltage. The charge that's flowed through the resistor multiplied by the potential difference across that resistor. Okay? So we can start to sort of play with things. We start to understand, exactly how this behaves. With gravitational fields, we know that we know a simple formula. We know that the gravitational field strength is known as the potential gradient. Okay. Sorry, electric field strength E. Just calling it gravitational field strength. I do apologise. Oh dear, it must be the morning. Now, so G is potential gradient. Okay. So the gravitational field strength is potential gradient. So the gravitational field strength, basically that means that it is d phi, which is the dr. Okay. Now, have you done differentiation in maths?
I'm sorry?
Have you ever done differentiation in maths?
I'm trying to like I'm started yesterday to learn this, but not yet. Like,
right. Okay. Well, this is actually a bit of calculus called differentiation. Now, what we've got here is we know that I'll show you a little trick, is D times minus G M over R dr. Now, when you differentiate something, you've got to reduce the power of this factor by 1, and then multiply it by the original power. So, for example, if you have y equals x squared, okay, whoops, I'll try and get that right, y equals x squared, then the derivative is actually going to be, take that 2 across, it'll be 2x, because it's x to the power of 1, okay? Here we've got r to the power of -1. So it comes out to be, we've got minus, because it's power to the -1, times minus gm over r. But if that's r to the -1 there, because it's divided by r, that then becomes r squared. Okay? The same thing happens with electric field strength. So if we've got the electric field strength, E is dV dt. So if we've got d here, we've got the derivative of minus q over 4 pi epsilon naught r. It should be dr, I do apologise. dr. Well, there we've got a -1, so we take out the -1. That's the power -1 becomes to the power -2 with q, oops, it's not negative, over 4 pi epsilon naught r squared, okay? And as it's a magnitude, we just ignore the minus sign and we end up with electric field strength. Does that make sense?
Yep.
Okay, so we can do all kinds of bits of maths with this, but basically, if you learn about the gravitational fields, you can learn quite easily about electric fields. And when we start to think about what's going on inside the inside a particular dome, inside say a round object. So let's take a hollow sphere. So let's take an electric field in a hollow sphere. Now, if we took a dome, like a round object, and we charged it up to a voltage of V, okay? So all the positive charge would be sort of concentrated about there, okay? If we think about it, the V here, the V inside here is constant inside, okay? It behaves on the outside like a radial field. Obviously, field lines go off to infinity normally, but I can't draw infinity on this piece of paper. So I'm just going to make the lines nice and long. So we've got a charged hollow sphere. Now, if we were to look at the potential difference inside that sphere, everywhere inside that sphere, that potential difference would be constant. Okay, that potential would be constant. So inside the sphere, we know that V would be constant. Outside the sphere, we know that it would drop off in the same way as it would always drop off if it was a point charge. Because there's no such thing as a point charge, because that implies things being infinitely small, which we can't have. So, on to the next part here. There we are. If we look at the electric field strength, okay, if we think about it, that is the gradient of that. So I'm just going to look at magnitudes really. So the gradient of this bit here is 0. So there's no electric field inside this hollow sphere. And then what happens is that the gradient then is outside the sphere. We then have a high gradient dropping off to a low gradient. I'm going to ignore the sign for now. It does exactly the same on the other side. Okay. Now, this means a lot of things. This means the electric field strength inside this sphere is actually 0. So if you imagine this a giant Van de Graaff generator, if you are standing inside it, you wouldn't know that you're inside an electric field. If you're standing outside it, you definitely know that you're subject to an electric field. But if you're inside, you don't. Now, this has a lot of different useful implications. One of them is the idea that if your car gets, if a vehicle like a car, which is insulated from the ground, if it ever has a power line touching it, so it becomes positively or negatively charged, or alternating current flowing around the outside of it. Actually, inside the car, as long as you're not touching the walls, inside the car, you're completely safe. And that's why one of the safest places to go sometimes in certain types of thunderstorm is actually inside a car or inside a charged a conducting structure. Because a lot of people say it's because the electricity sort of conducts around the outside of it. It's kind of true, but the point is that actually what happens is the electric field inside remains 0. So there's no force on any charges, so you're not going to have any of the ions in your body trying to move about, and therefore no current through your body, which means you don't get an electric shock. So there are lots of different sort of implications for this. Another classic example is just when you understand that if you have if you've got 2 parallel plates, the other proof that it's the potential that the electric field strength is potential gradient. If you have 2 parallel plates, let's say we're positive up here, negative up there, you can start to analyze what's actually going on. Well, you know that you have an electric field going from positive to negative. You've seen this before. Now, if you imagine you're going from positive to negative, or negative to positive, let's say that we're going from 0 to 1,000 volts of potential difference. What actually happens is if we're going up to plus 1,000 volts here, if we try to look at the force, we know that as we're trying to move up in this direction, which I'm going to call X, where that is D, the distance between the 2 plates. If we were to measure the electric field strength between the 2 plates up from 0 up to a distance X, then what do you know, Dennis, about the electric field strength between parallel plates?
Constant. They'll be constant.
It's constant. Excellent. So from 0 to D, that distance D, we know that electric field strength is constant. Okay. Now, as the electric field strength is the gradient of the potential, if we were to measure the electrical potential compared to X up to D, well, we know that when we get to D, we know that when we get to D at the top here, we know it'll be 1,000 volts, or the maximum voltage. Okay, the voltage between the two plates. We know that when D is 0, the electrical potential would also be 0. So we know that point, and we know that point. And if the electric field strength, Dennis, gives you the gradient, and the electric field strength is constant, what can you tell me about the gradient of this line?
Gradient.
This value, the electric field strength, is the gradient of this line. What do you notice about electric field strength is constant. So the gradient's constant. So what type of line on the graph, Dennis, has a constant gradient?
Oh yeah, from 0 to like
The voltage.
yes.
Yeah. So is it going to be a curve or a straight line?
Curve.
Gradient is constant.
I guess curve, because like it's not a straight, like it's straight line, but
Straight line, Dennis.
yeah.
Said that the electric field strength, we know the electric field strength
Yeah.
between two parallel plates,
Yeah.
okay, is a constant. And the electric field strength, its definition is the potential gradient. In other words, it's the gradient of the line that's going to go from 0 to the maximum voltage.
Yeah.
And if a gradient is constant, it's going to be a straight line, isn't it?
Yeah.
Okay. So we'd actually expect a straight line, not a curve here. Now this tells us something very important. If we want to look at the potentials, what we call the equipotentials, we want to draw a line which shows every areas of the same potential. We know that those equipotentials are going to be at right angles to the electric field, and they go up evenly. So a quarter of the way up, you'd have 250 volts, 500, 750 volts, okay? So those equipotentials, they're called these equipotentials, these lines where the potential is equal the whole time, the voltage goes up linearly with distance for parallel plates. Using the same physics for a radial field, we charge something up to a voltage V. We know the electric field will be like that. Sorry, one last thing with this last bit. Obviously, this is the gradient, so this gradient gives you electric field strength. So the electric field strength is V over D, maximum voltage divided by the distance. And that's why that formula works from our previous topics. So just to finish off, if we got a radial field like that, if we were to look at the voltage versus the distance, so I'm going to go for the radius of the planets of the object is there, let's say, and we were looking at the voltage, the potential. We know the potential would be constant, and then it would drop off over proportional to 1 over R, okay? So if that's the potential, we know that the E, the electric field strength, would be proportional to 1 over R squared. So it's not going to be linear, it's not constant. So as it's not constant, if you draw evenly spaced equipotentials, your first equipotentials are very close together. And then as you go further out, your equipotentials would spread out if they're going up in even steps, sorry, going down in even steps. Okay, does that make sense?
Yeah. Yes.
And that's just 2 bits of etiquette for electric fields. Right, I think we'll end there, Dennis. What I'd like you to do, if you go and show my homework, you'll see that there is a Seneca exercise for you to do this afternoon. So your afternoon project is to get that Seneca work done, okay?
Okay.
Okay, and I'll look forward to seeing your marks, and I'll feed that back to you. I think I'll see you next on Friday, so we'll feed that back on Friday. All right, right. Take care until then.
Okay, thank you.
Okay, bye.
Bye.